Okay, so let's start with the talk of the day. It's a more technical talk related with the extremely large telescope and all the wavefront control, focusing on the phasing of the primary mirror, the cemented mirror. The talk will be given together by Jason Spiromilio, that is the ELT scientist, and by Michael Esselborn, that is part of the system engineering group in charge of the model of the telescope and all the phasing strategy.
Thank you very much. It's fun. So what we thought I would do tomorrow, I'm giving a talk about the whole thing, and this is not a status thing, but this is really focused engineering talk. And we realized that it may be useful if I give you some principles of control before Michael will focus on phasing. Okay, just the phasing of primary and a few other things that we use. But what underpins all of this is a little bit is relevant because some of the decisions are complicated. So this slide, for those who will come tomorrow, we'll see this tomorrow as well. But go very quickly through this. But fundamentally, the telescope is very difficult, partly because it's big. It is not complicated and it's not complex. It is just very, very big, which makes it very, very difficult. You can choose through control to make it complicated. And the effort, and this is what these few slides at the beginning again do, the effort is to not do that. Okay? Because we don't know yet what the instantiated telescope will look like. So if you start complicating things and making multiple loops before you know what the system will actually be like, you are solving problems that you don't know the size of and the scale. So this is relatively important. Because we've been talking about AO, et cetera, all AO systems on 4-8 meter telescopes are working in a perturbative regime. Okay? The small deltas on top of a very nice, quiet system. Okay? This is, you can see this, but very, very simply, somebody puts a bench and puts something on a bench. Okay? You can test that bench in the lab. Okay? The telescope is not a lab on the other side. So in the case of the ELT, and these are a few slides that are going to follow, you can't work this way. Okay? You can't just say the telescope is going to be benign and move on. So this is relatively important. So if you move away from this regime that we understand, there could be dragons out there. There's physics that we have not probed. We don't have a gut feeling for. So this is an old map where, what was at the edge of the map was there were dragons there. We don't know. So if you fly from Crete to the north of Greece, Crete is in the south of the islands, you pass this island, which is a dragon that Zeus slew, and it ended up being a stone in the sea. So there are dragons. They are real. Okay. So this slide you will actually see a number of times in various presentations. I will show it again tomorrow. I think Michael has it as well. This is there because it actually gives you the scale of the problem. And this also matters, okay? The deformation of the back structure of the M1 is 5 millimeters. Okay? So that's what's actually moving under your M1. The front surface for all of us is exactly the same. It says to be at 10, 100 nanometers, some magic number depending on what wavelength you're going, but it's nanometers. The back here is changing by 5 millimeters. Your front problem is the same. The back problem has actually become maybe an order of magnitude larger or 2 orders of magnitude larger, depending on how big or small your telescope was. Okay? The deflection of the secondary down to the relative motion of the secondary to the primary is 5 millimeters. Okay? This is an f.9 primary mirror. You move the secondary by 100, 200 microns and you're dead. the aberrations explode continuously. So the scale of the problem is again very large. The size of the primary is such a big scale, it's 1,000 square meters. Okay? So the airflow across it alone, the pressure pattern, again, the front surface, the wavefront has to be the same problem we all have, okay, nanometers. The pressure on the primary gives you microns, and that's dynamic. Okay? And if all of that was not enough, if you have a little cryo cooler on the system on the side, and it just goes boing, 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 okay, that's the cooling thing for the lasers on the side of the primary, messes you up as well. So it's a dynamic problem. This is not a static. This is the telescope. I'm not talking about the atmosphere. I'm not talking about doing it. This is your plain telescope. Once you go to this size, it is not a static problem. So the reason we dared to build this telescope, because we knew this is not, this part did not come to us as a shock, is you actually are dealing with a dynamic problem. So the telescope has an adaptive mirror in it, not because you fix the atmosphere and you make small stars and all of that. That's a side thing that you fix for fun on the side. What you have to digest is the entire telescope. So if you actually compound all the various factors, the ELT is about 10 to the 6 to 10 to the 8 times harder than an 8 meter. Right? The time scales are at kilohertz. The deviations are in millimeters, not in microns. Right? So you compound all of these things. This becomes a dynamic problem. So the bottom line there is, it's an adaptive telescope. It's an adaptive telescope to fix the telescope. Okay? The other thing that is very important here in terms of alignment and everything else, we do not believe that we can achieve static alignment. So everything is on hexapons, including the M5, which is not supposed to move at all. Okay? It's actually on a huge hexapod and can move around. Okay, so this is a preamble. So Michael is going to talk about the phasing station, phasing diagnostic station. Part of the telescope side is how to capture all of this to actually get to the point where somebody can do phasing and can do other stuff, and that's can come. So I have one more slide, and then I will stop. I have many, many slides we can discuss possibly in the afternoon in some meeting room, but Michael should be talking. We actually, this is in the control principles, and that has informed all our sensing and all our command. Oops, all right, that's good. We do not extrapolate, we do not infer the property of a system from another system. Trivially, I do not determine how much coma I have in the telescope by knowing the decenter of the primary to the secondary. I do not do. I measure coma. I never, ever, once you've built the thing, you can do whatever you like, because then you see what it does and you can do whatever you like. But when you're designing it, if you assume that it's going to be that by knowing where the secondary is and knowing where the primary is, you will know how much coma you have, and the telescope does not manifest itself exactly the way you thought, you're dead, because you don't have the sensor. So at this stage, before first light, and for the last 20 years, no matter how clever a technology somebody comes and says, I have a laser tracker that can tell you where all the optics are, and I can tell you exactly where everything will be, the answer is no. If you want, I will put an interface plate, and you can mount a laser tracker there, and I'll pay for 11 laser trackers if you want 11 laser trackers, and you can have software people write it, but I am not using it. This is, we observe the state, and we fix what we observe. And this is a requirement on all the systems. We do not control outside that space. So if you think you need to control 5,000 modes, you measure 5,000 modes. You don't measure 3,000, say the other 2,000 are going to be the same as the other ones. We never do. And this is a constraint set, maybe philosophical or whatever you want, which Michael and all the wavefront sensing team have to live with, the mechanical guys have to live with. You do not, if you can't see it on the sky, if you can't see it, then we're not moving. Okay? When it's built, you can do whatever you want. And this is, you'll see some decisions in some of this conversation that we'll be having here. Why do you do this? You could do this, you could do that, you could do the other. I don't know what the final system will be. The rest of the slides, we can, if we have time or you have questions, we can go through that. I think Michael should present things that are actual engineering as opposed to philosophy.
Okay, so I continue with explaining you what are our plans for the new wavefront control strategy in terms of phasing, coherencing, Shack-Hartmann registration, essentially. About 10 years ago, we've had the chance in the course of having technical time access to the GTC to actually test and learn those strategies. And if you see how our baseline design looks like, you see probably a lot of similarities. I'm starting with the, this is our entrance pupil. That's an image of the M1. M1 is the aperture stop. There's no optical element for it. So it's indeed also the entrance pupil. We have a collecting area of about 1,000 square meters. You also see the spiders that are not as thin as yours. They are about 200 millimeters thick. You see 6 identical ones. The lower one is though a bit thicker, and this is the M1 segment crane, which is used to manipulate the segment exchange. Yeah, on all 1,000 square meters, the total obscuration is about 30 square meters. So we need to phase. So our telescope is, of course, subject to various error sources. So quasi-static ones, dynamic ones. This is a slide showing you how big our quasi-static perturbations are. This is the effect of gravity acting on the telescope tube. So you see the M1, M2, M3, M4, and the M5. You're actually standing at the Naismith platform right now and looking into the beam. So that comes towards you. This is the M5. It's not there visible, but it's within the M1. So if we now move the telescope from taking it from zenith towards horizon, this is what you would see. Note that your view is co-rotating with the altitude. So it's essentially this deformation mode. This is a result from finite element modeling. You see quite a strong deformation of the M1 back structure. All the mirrors move along, so there's quite a great deal of common motion. There's a specific mode of the telescope alignment that grows and with gravity. And yeah, the translations are of the order of 10 millimeters here. Rotations are 100 arc seconds. So this is what gravity alone does. And on top of that, there'll be other quasi-static errors, temperature deviations or dispersion of temperature in the dome, and so on and so forth. So, and this we need to take out by defining the edge sensor references in order to flatten the mirror.
I think when you show this plot, just a thing, you should tell them what the scaling factor is.
That's a thing, indeed. It's 1,000. So it should look more right-wing than it is. This is also some results that Jason has shown, also finite element modeling, control modeling on the M1. This is the effect of quasi-static wind. We have 10 meters per second outside wind speed that we baseline those analyses on. These are quite fast, of course, and of course they can't be taken by the phasing. This directly goes through to the SCAO loop or the other adaptive optics loops, and is taken by the M4, which gets out the shape of the wavefront, and the M5, which take the tilt out of that. So low orders, high orders, printed not to the same scale, but actually they add on top of each other. deflections are of the scale of microns. So this brings us to the task of the wavefront control for phasing. So we essentially need to minimize the surface discontinuities because these will actually harm the AO. So if you have any AO instrument post-focal, this will happily take out the low orders, but you're left with high orders. And this is the aim of phasing. Otherwise, we need to preserve the stroke. So we do this by offload mechanisms. In principle, you offload stroke from fast actuators with low stroke to slow actuators with large stroke in cascade. And having done those two things, should be in good shape. So this is a functional representation of our PDS. So PDS stands for Phasing Diagnostic Station. The PDS holds all the sensors that are used for phasing the M1, phasing the primary, also for verifying the performance in SAO, so verifying top-level requirements. And you see it's split into two regimes. You have the upper part, which is the pupil plane, the lower part is the image plane. So we have, all in all, we have 6 sensors. It's like a Swiss Army knife. We have sensors in the pupil plane, in the focal plane, in the visible and in the near infrared and infrared. We have 2 phasing sensors. One is the Shack-Hartmann phasing sensor I'll show in a second. The cervical phase contrast sensor is our plan B because there are risks associated with the Shack-Hartmann sensor in terms of registration, pupil motion, and so on and so forth. All the things we're discussing right now with you. But those risks are not present in the cervical phase contrast sensor. This is why we have it as a plan B. We have in the middle row our adaptive optic sensors. This is a pyramid sensor, verifying the high-level performance requirements. And we have a low-order Shack-Hartmann sensor. Essentially, this can be seen as a fourth guide probe on axis. We have an imager plane, so we have a near-infrared imager and a visible imager. Yeah, and these, of course, are important for the technical positioning, where we make extensive use of them, that's for sure, but also in operations where we recurrently need to phase the M1. So our baseline is phasing every 2 weeks for a contingent of 2 hours. Yeah, this is the operational part of that. So this is where the PDS is located at. So you see, again, detail of the ELT. You see the M1, the adaptive relay tower holding the M4, the M5. And light is propagated towards the right, where the phasing diagnostic station is located. And I can point, but you probably can make out the optical propagation. There's a fold mirror, which is our M6. So after M5, M6, directing the light into the phasing diagnostic station, which is here depicted by the blue frame. So this is the subunit of the telescope that holds all the 6 sensors as a visible, plus a visitor port. So briefly for the phasing diagnostic station and relating to the phasing, we do have to have a beam propagation mechanism that includes the functions of beam steering, so or pupil steering. This is, well, if you go on the left diagram, the light enters here from the right. It's directed by this pickup mirror into the highlighted box. There's a pupil steering mirror, there's a K mirror pupil derotator, and then the light is propagated towards the towards the Schatz's assembly, which is on the right, going through a zoom. So, and here we have quite large tolerances or quite large actuator stroke, because commissioning the pupil can be anywhere. Though high resolution, so the resolution needs to be way larger than, way smaller than the tolerance in the overall registration budget. So we can move the pupil by 7 meters in left, right, up, down, and we can actuate it with an accuracy of 0.7 millimeters in the M1 space. We have pupil derotation. The function is the same for pupil rotation, of course, and the pupil magnification, which is done by the zoom optics with plus minus 3.2% the pupil diameter. The Shack sensor looks like so. It is co-located in the visible part, parallel to Shao, which is the Shack-Hartmann of the adaptive optics sensor. So in Shapps, we use that for segment capture, segment stacking, coherencing, and phasing. Actually, it's a scaled-up version of the GTC solution. We kept the same pixel scale, 0.2 arcseconds per pixel, scaled it up with the geometry of the ELT Pupil, and you'll end up with a 4K detector. Okay, we could have even gone a bit larger. TMT is baselining an 8K detector, but we went for this solution. Pupil sampling is you get 10 millimeters per pixel. Then you see there's a plane where filter wheels are located. We have various color filters and also neutral density filters in order to tweak the exposure times. Importantly, we have not only one density array, because there are pros and cons of a given solution. You have two, and in an empty space, we have baseline now 3 density arrays and an empty space. But the mechanism holds up to 4 density arrays. Yeah, and it's being built. It is already aligned. You see here, this are pictures taken a couple of months ago, where you see the Shaps assembly being open and being assembled. The view at the bottom is you look from the camera into the system, and you can make out the Lancet positioning systems with its 4 openings. Yeah, our phasing and coherencing strategies are mainly inherited from KEC and GTC. So we had, as I said in the beginning, we had the chance to work at GTC in order to test various strategies. We baselined 2 procedures. This is coherencing and broadband phasing, and it's bicolor phasing. In coherencing, your dominant, or your more important metric is not the phase, but the coherence. So first, you want to see where are we with respect to the coherence of the filter. You want to position your segments in pistons such that they come into the coherence of the filter in use. The phase is at that step not actually important, but when we do broadband phasing with using the phase, we use the position of the coherence, so the position of the maximum contrast, in order to solve the 2-pi ambiguity, because broadband phasing only uses 1 wavelength. If you go with a single wavelength, of course, you're subject to the 2-pi ambiguity, and we solve it by locating the white fringe. Bicolor phasing uses 2 wavelengths with narrowband filters, so we have ultra long coherence range, like 50, 60, 80 microns. But we know that we're coming from a state where we already are coherent. So the baseline assumption for using bicolor phasing is that you are in the range of the effective wavelength is the product of the 2 numbers divided by the difference, and this is about 2.4 microns. And you need to be within plus minus λ², so you need to be at plus minus 1.2 microns. You make sure you're in that range, you can use that technique. It is way faster than broadband phasing because you only take exposures of 1 and the second wavelength, and you're actually done. But you have to be sure you're in the capture range of that movement. So you notice this. This is our baseline for one of the arrays. We have 3 of them. This is a replica of the SFS2 of GTC with some modifications. We've noticed that hexagonal inner sub-apertures, of course, is effectively or efficiently sampled the hexagon, the segment. You get more light, but on the cost of interference with the neighboring phasing sub-apertures. And that gave us a hard time. We did a lot of modeling to understand where this problem comes to. We attribute it to interference, because if you use hexagonal segments, then of course your diffractions directly propagated to the phasing sub-apertures. And this is something that we wanted to avoid. Therefore, we go to circular sub-apertures. You see, okay, they are also smaller, okay, because at GTC there was a large photometric ratio a factor of 6 or 7, I believe. So we already needed to come to the saturation limit of the inner step apertures in order to make sense of or get the phasing signal. You notice a third, so the phasing sub apertures are the same as yours, exactly with the same dimensions. So it's a double slit with a separation of 30 millimeters, because if you don't have that, you are already sensitive to registration errors from 0. So you should have a central bar that obscures the segment edge, and you have more modulation fringes in the coherence envelope. So there's a good point to have this. You see there's a third pair of subaperture types at the outer peripheral of the M1. These are rectangular boxes. These are registration subapertures. So M1, as I said, is the influence pupil. You have complete visibility of the outer and inner contour, so you can make sure that you can make use of that signal. And these are the guys that measure that. But essentially, yeah, it's coming from SFS2. We not only have this one, we have 2 others. At the left, there's a solution that is a candidate or a specialist for phasing. Okay? So with the left one, we have 2 phasing subapertures per edge. We have 6 inner subapertures that look like phasing subapertures, but they measure tip and tilt and also focus. Yet the inner subapertures are also directed, so their diffraction does not go into the phasing subapertures. Yeah, that was the rationale for this one. The middle one I've just explained. This is our workhorse. Yeah, we have the capability to measure phasing, stacking, focus, astigmatism, and trefoil, and we keep it with those modes because we can only actuate these modes. Yeah, so we have 9 warping harness actuators. We can do a bit more, but they're getting more and more stiff. So we baseline for actuation of focus and astigmatism, of course, and perhaps trefoil. And the array C type is a bit of a compromise. So we do have, again, phasing subapertures, 2 per edge, and we have 7 inner subapertures. So with this one, we measure phasing, stacking, focus. All of them have in common that we do the stacking and the phase measurement in one go, which I think is important. Yeah. Another detail we've seen with spiders. So if I toggle between the 2 frames, you see that. So the spider will actually go along the Y direction, and we can put the phasing subapertures a little aside. So we offset them laterally in order to make use of them, because otherwise they would be impaired by the spider and partially obstructed. And we said, okay, we can position anything anywhere, so we put them just aside. Okay, and then just the principle of coherencing is what you do as well. So we ram the 2 adjacent segments on top of each other. The light is propagated and combined by the phasing subaperture and forms this interference fringe. So if the distance in piston is larger than the coherence length of the filter, which is just now the case, you get an incoherent spot. And if I play it again, if you now come in the vicinity of the, so if you level out the pistons, then you get signal, and now you lose it again because you're further away than the coherence limits. In coherencing, again, we do not measure, or we don't use phase, but we just look at the contrast of the fringe. And also, this is demonstrated at GTC. We use a specific scan trajectory. I think that also came from you, yeah, where you have a color code. So that means a segment of one family or of one color doesn't have an adjacent neighbor with the same color or family type. It's depicted here. And then you can heavily parallelize your trajectory. And the feature of this very trajectory is if you audit all your steps, every subaperture, every phasing subaperture is exposed to the same OBD. And then playing the trajectory on the M1 looks like so. Does that run now? No, now it runs. So 27 steps will excite all the phasing subapertures with plus minus half the coherence length. And you go through the coherence for all of them. in the data reduction afterwards, you just sort them and do the data reduction. I play the movie here. If you, this is just a scan applied. Left is an ELT scale Shack-Hartmann frame, and then there's the data reduction. If you just look at the Shaps frame, what you see is that only the phasing signal varies. That's for sure, because we don't include tip and tilt. There's no atmosphere. So the phasing signal changes. So we have 4,500 phasing signals. So 4,500 interferometers. What we do is now in the data reduction to cut a box at the centroid of the phasing signal, and then collapse the 2D into a 1D profile. So this is the step you see there. So you get the 2D signal, you weigh it and interpolate to get the orientation right, and then collapse it to 1D profile. And the phase is encoded in that profile. Okay, the phase, the coherence, both properties are encoded in this profile. And stacking this over the duration of the scan would give you the this waterfall display. So this is quite a nice visualization of the coherence, that we can leverage then. For measuring contrast and measuring phase, what we do is we project this profile onto a library. For all sub-apertures, we have a library of what we call ICS modes. ICS modes is nothing but the DC term, the cosine and the sine modulation, so the main modes of modulation for this interferometer. So projecting this will give you the CS coefficients. Using the arctangent, you get the phase, and using the square root of using the norm of the sum, you get the contrast. And if you then plot the contrast on this waterfall display that was on the slide before, you can directly tell, okay, this is the evolution of coherence. If you have a top hat profile of the filter, of the color filter, indeed you get a sync function, and you fit this, and you get the position of the OPD. Yeah, and then you iterate this. You do it. You start with a narrow band filter with large coherence to come up to a broadband filter with low coherence. So iteratively, you refine your coherence resolution. Bicolor phasing, as I said, uses two colors. And you just need to make sure that you are within the capture range of that procedure, which is plus minus half of the effective wavelength. Okay? If you're there, you can use that. And doing this is more time efficient because you only have frames at one color, frames at the other color that you modulate with two sky frames. And if you modulate 3 times color 1, modulate 3 times color 2, have 2 additional phases. This makes 8 frames. And we had in 2014, we tested this procedure, and we could run this 5 minutes was this procedure length. And you see here this is much faster. It's similar to the broadband phasing, but with a reduced trajectory. So how do we determine the phase? This is a bit involved, but it's if you have 3 diagrams here, if you measure 2 phases, and you know that you get a solution over your effective wavelength, plus minus 1.3 microns. The effective wavelength is expressed in the phase measurement is the left plot, where you plot 600 degrees minus to 600 degrees plus in one phase and a little deviated phase on the other one. Now you know as you measure phase, this can only be in the interval of plus minus 180 degrees. So you need to break this branch, and you get this diagram in the middle. So you wrap it into the phase space. And you know that if you had perfect measurements with no noise, all your measurements need to land on one of those branches. But of course you have noise, there are errors, and it would look like so. So what we do with this is, for every point, we have 168 measurement points, 168 phase measurements. For every point, we find the closest position on this branch, and we know this should be the position where it is. And we can interpolate to find the OPD, and the dispersion around the ideal branches will give you the noise of the measurement. So that's bicolor phasing. There's another technique how to derive phase, and we are talking to TMT and tech guys, and they've invented this. So this is based on pattern matching. The idea is that you pre-compute a library of PSFs for specific OPT steps, and then you measure something and you cross-correlate with this library in order to find the best spot. And the best spot in that library gives you the phase measurement. This is a simulation, just describing the procedure. So the first images, so lib1 to lib11, this is your image library. So you apply phase steps to your interferometer, you record the response, put it in library. The other one called feature, this is your measurement. Of course, you need to first get the centroid, you need to rotate it, interpolate it, and what you do is then, so for the 11 images, you just convolve it with all the images and compute the normalized cross-correlation coefficient. So the whole thing is, of course, is a harmonic function. It's an interferometer. So, of course, the resulting NCCs, so normalized cross-correlation coefficients, lie on a sine curve. This gives you enough leverage to fit the sine over the library and determine the best retrieve position. That's really nice. So it's a super robust, so making analysis, including noise and well, photon noise, going to very low SNR, it really gives you a good results. An ongoing piece of work is now that we adopted from CAC. Okay, they came up with that many years ago. I should say we are not so sure whether or not we lose information when we collapse this 2D to a 1D profile. So therefore, this approach is appealing because you stay fully in 2D. And I think this is, more robust, I would say. The ongoing piece of study is where we have all the GTC's data still available. So we go back to 2014, so 12 years ago, and we project this, where we measure it, on this library, and then see, can we make sense of the data? And indeed, now this is data coming from a procedure with 27 steps. The very first one I showed you, broadband phasing. So you modulate the segments and you get the signal. And this is how it looks like. So for all the 27 steps, what you do is a convolution to the image library and recording the NCC coefficients. So it looks like so. What you see, the feature goes through the 27 steps. It starts at a very low coherence and it would end at a very low coherence. The coherence itself is actually just the amplitude of that curve. It's the maximum minus the minimum NCC coefficient. This is a measure of coherence. But what I want to show is that indeed there's clearly a signal in. There would need to be, we would need to make some adaptations. I'm not sure about the plate scale actually. But I think this is quite robust and promising. And this is why we want to include it in the retrieval. Yeah. This is just the outcome of that template. It shows you a contrast curve, bit noisy, of course, but still there are certain things that are not yet implemented in that experiment or in that simulation, like finding the centroid, validating the plate scale, and things like this. But there's signal, you can retrieve it, and if all what you do is to compare it to your baseline, you still get some more information. Okay, so talking about registration. Now, this was coherencing and phasing. Registration is the crucial prerequisite for all these things that we do with the Shack-Hartmanns. If we don't do that, we cannot actually go one step further. So registration, we have two methods for that. So this is one, the incoherent method, where we got to learn from Javier, and the photometric method that we can do because we have visibility of the edges. Again, the Shack-Hartmann design, I would just mention again, the central obscuration of 30 millimeters in the center. And then the idea is clear. So we move the pupil positioner in the direction along the gap, so orthogonal to the edge. And you start with an interferometer on one segment, you move over, and you stop at the other segment. So you start where your phasing aperture is coherent, you go over incoherence, and then end when your phasing subaperture is again coherent. And your job is just to identify where is the center of that transition. And this gives you, for 4,500 subapertures or 186, it gives you the local registration measurement. It's not a global one. It's really per phasing subaperture. It gives you the local registration error. Yeah, you see here, this is the transition then from coherent, incoherent, coherent. And there are various methods how to best detect the center. Yeah, I think, yeah. And then in the upper bars, you see that there's indeed a deadband, and this is why this is also needed. I think if you don't have that deadband, you're virtually no tolerant to registration loss. So this is why we want to put it in, of course. GTC configuration, we have 3 edges, 3 scan directions. You can go with 1 if you liked, because also if you just move vertically, also the other directions would be excited by that, or would face this, but they move a bit slower. Yeah, not so nice thing is, of course, this is wavelength destructive. Okay, so you would have to put a step of a couple of microns at least in order to make this work. If you're really well phased, you want to do this. So, and it takes a lot of time because you have to sample in 3 directions, your pupil positioner. So we had something like 60 scan steps or so. This really was actually the longest template. So another method, yeah, just quickly, okay, you have all those measurements. You can do more than just lateral position XY on scale. You can do the rotation, the scale, and the stretch modes, the scale. At ELT again, and one is the pupil. So we've seen the outer and inner peripheral subapertures that measure the normalized intensity. And we can use that signal in order to do registration, not only like every other hour, but really frame by frame. This is the big advantage, and it's not wavefront discount. You see in orange, the outer and inner peripheral registration subapertures. The green ones are important as well because we normalize the flux to the adjacent inner ones because of there any segment reflectivity errors or any other error source. Normalizing it gets you more robust. You can build in simulations a model for that, which is the response, or which shows you the error signal as a function of lateral X, Y, scale, and stretch modes and rotation. And then this is how the signal looks like. So in a simulation, we can, in the left plot, we can apply a very small registration errors, and the bars are here plus minus 5 millimeters. The photometric signal in a spatial scale, which looks like the upper right plot, and then flattened as a vector is something that you will detect. And if I play the movie, you see what's happening. So we're moving in this lateral registration space. You see that the photometry actually changes in the upper right plot. And also the flattened vector, this is the signal that you get. And this is what you project on your control matrix in order to derive the XY position, the rotation, and the scale. And in our case, those 4 parameters will be corrected for by the PDS pupil positioner, pupil rotator, and zoom. And this is robust as well, accurate. This is the applied and the derived errors. So this is what you would get with this method. Yeah. Reconstruction strategies, maybe just quickly. So we measure with the Shack-Hartmann, we measure the phase because it's a modified Shack-Hartmann. We measure tip tilt. We measure certain segment shape errors. So we have astigmatism, 2 modes. We have trefoil, which is not noted here. It's not part of that study. And we measure focus. What we can actuate is, of course, with pucks, piston tip and tilt, and with the warping harnesses, astigmatism in both directions and the focus. So you can construct various interaction matrices to get various control matrices. Depending on what you will include in your control system, you get a bigger or smaller matrix. You can, on the x-axis, there are observables, so phase measurement, tip measurements, astigmatism measurements, and focus measurements. And then on the y-axis are the reconstructed properties or quantities. And then just qualitatively showing what happens if you choose one strategy or the other. If you only have one segment that is deformed, otherwise everything's perfect. One segment here is highlighted, has astigmatism. Okay. If you just measure the phase with the 12 sensors and then try to reconstruct the piston, the tip, and the tilt, you end up with the upper right part. So the perturbation propagates through the full mirror and excites low orders, of course. It's the propagation of this error. And you end up with a high low order deformation of the mirror. You want to avoid this. You not only measure the phase, but you measure the stacking as well. And then you're complete for PTT reconstruction, but yet you've not identified the astigmatism of that segment. Only if you did the full inversion, so measure piston tip and tilt, measure phase and stacking, I should say, measure astigmatism and focus, then you can do a perfect reconstruction. So in the ideal world, you would completely isolate your errors. Then we're making, because we cannot assume that we only have one erroneous segment, but we put all the noise on all the segments, and then we try to identify a complete but also robust approach in order to iterate this. You see, all the simulations end up with a very different reconstruction. Yeah, and then you can say, okay, on top of that, as what Jason explained, we have this AU loop running. So we are not left with this because we close the scour loop on that. And the scour loop itself will measure, correct it in the upper right plot, of course, very nicely. And then using the offload mechanism, it would also push this again to the M1 in order to heal itself. So these reconstruction schemes are quite involved. Local coherencer, I think, have you mentioned that? Not. So this is our phasing gun. We've seen Bana the day before yesterday. Ours is called local coherencer. It's a device that we deploy as a payload on the M1 segment manipulator that moves on the M1 segment crane. So the M1 segment crane is the crane here highlighted in blue. So it has a segment manipulator that is used for replacing segments, and it can take another payload, which would be the local, so the local coherencer. So once a segment got replaced, you would exchange the payload, will attach loco, will go to that very same place, and loco is a device that measures the replaced segment within the vicinity of the not replaced segments. So if the reference is fine, loco will put it with respect to this reference. It looks like so. This is in the integration hall. You see the dimensions. There are, as I said, there are 6 sensors mounted on this, replicating the M1 segment geometry. And then the concept is like so. It's a wavelength. It's an interferometric method. It first measures the orientation of the device with respect to one of the segments. This is a pointing camera. And then with an interferometric, you see a Michelson interferometer here. With this interferometric approach, it measures the position of one segment with respect to its neighbor segment. Yeah, and there are also other helping functions like edge detection and so on, which I do not mention here. What they've done in order to increase the capture range, because we're talking here about a couple of hundreds microns of positioning tolerances. So the mechanical position goes in. We should say, okay, give us a capture range of, it's mentioned here, more than 250 microns. Okay, what they did is they need to create fringes, so they have this prism, but they also added on this prism a step function, and this is separating the interferogram in 5 zones with specific offsets, and thereby increasing the capture range. So the fringes look like so. You see in that left plot, you see two of them. Actually, it's the same response, but since the OPD has overlap from one zone to the other, it appears twice. But this is just to preserve that there's a continuity in the measurement. Yeah, this is what it does. And then you see, for instance, I think the middle segment, you see 5 zones corresponding to the 5 steps of this step prism. Ideally, it should land on the middle one in the center. Okay, so that would be a phase position. If you have this, then the interferogram looks like so. There are many, many fringes in that envelope, like I think 30, 40 fringes inside. We're trying again make a coherence measurement. That means we're trying to detect the maximum of that curve, and we fit it to Gaussian, detect the center, and the key performance requirements was 300 nanometer at the surface. So this is 600 nanometer at the wavefront, and this is 2 sigma. Once we are there, we can directly apply the bicolor approach. So that was the promise for that. It's an enabler in operations. Yeah, if you're there, if you have your system under control, you just need to deal with the residuals of the replacement of the segments. If you're within 600 nanometer, then you are good to go with a short, very short bicolor phasing measurement. One word about SUS. SUS is, again, this is the very, very important plan B. So if it turns out that the pupil registration is not manageable because there are very large, or there are larger distortions than there are than the budget, then okay, we have the risk mitigation in place. We will just make a new Lancet array, but in that time and maybe before and after, we use that sensor. So SUS stands for the Cernic phase contrast sensor. It's conceptually easy. You have in an intermittent focal plane, you have your Cernic plate and a field stop, and then you recombine the light into the propagated back to the pupil plane. And what you see is that phase steps will turn up as intensity steps. That's your signal. We have various plates with different diameters. So this is a measure of how large laterally the signal extends. Yeah, we're using this. The nice thing about that, it's completely non-responsive to any pupil registration errors. There's nothing that you would register to. You make your measurement, you detect from the signal, you can find photometrically the pupil, you have enough segment edges that you can say with high accuracy, where is my pupil, extract the pixels, extract the signal, and you're done. Only thing is, this works in H-band, and therefore we have more fringes in the coherence envelope. This is a measurement on MELT. I haven't mentioned MELT. MELT is one of our test benches, where we have a segmented mirror on, where we have a DM on, a field steering mirror, and actually a functional representation of all of our phasing, of all of our PDS sensors. So this is in place. It's a laboratory test bench, and we exercise our phasing strategies, wavefront control strategies, and of course the concurrent development of the control system. So this is used by many parties, actually, more than 2. What you see is stepping the segmented mirror in piston, and you see a nice SUS response. Yeah, and it would be ideal just to go there and detect the pupil position, extract the signal, you're ready to go. Lessons learned. So I said, at GTC, we had the occasion to really test and try, experiment with the phasing strategies, but also shaping and M1 calibration strategies. So it was very, very useful, and really gave us the opportunity to have really hands-on experiments on a real system, not on a test bench. And that was really valuable. And with baseline, actually, you see the design of the Shack-Hartmann is very similar to what we had at GTC. So we made relevant changes to that, but we adopted pretty much of them. Okay, as I mentioned. Yes, and it's not only the technical aspect, but also operationally, how we would go from one step in the commissioning sequence to another. Like we at one mission where we played through segment capture. So we exploded M1, scene was bad. We could do this. We exploded the M1 and then scanned the main axis, try to identify the best place for a segment. This is something that you would do in commissioning when the segments are in with mechanical tolerances, and you would need to find them in the first place in order to propagate in your sequence. So also this operational and procedural knowledge or experience we got from here that was very helpful. And lastly, it helped us to define our phasing strategy from start to end. So we do one step at a time, simple and robust. We capture, we stack, we shape, we register, coherence, and phase. And therefore we have the difference options that I mentioned. Yeah, I think this is my last slide.
Questions? There's one fast related with the narrowband technique that you will use just for the fine phasing, let's say, once you have used the broadband approach. Why have you decided to use only 2 filters? Because at the design moment, you could have added more filters.
We could use more. We could also use not this geometric retrieval that I showed with interpolate, so finding the closest position to the branch, interpolating this. We can also use a chi-square approach where we identify what is the best solution with 2 or 3 filters. Indeed, this is an option, but we haven't actually exported it further. So the option is there. Whether or not it makes it more robust is really a detailed discussion. So because you can extend your synthetic wavelength or the capture range, thank you. You can extend that on the cost of robustness. And this is something there, but of course the option is there.
Stop here. I have many questions, but maybe we can. Okay, so thank you again very much.